and foremost, the objective of this study is to determine whether the distribution of GPA, ACT scores, and high school class rank follow a normal distribution. Second, to evaluate whether there is a linear relationship between academic performance indicators and university admission trends. And the third one, to determine whether the effect of ACT score on GPA changes based on a student high school class rank. Next, I would like to explain the data description. The dataset used is related to university admissions and includes performance indicators such as GPA, ACT scores, and academic year of application. The Director of Admissions at a state university wants to determine how accurately students' grade point average at the end of their freshman year could be predicted by entrance test scores and high school class rank. The dataset contains 705 observations related to the university admissions and contains 5 key variables, which is ID, GPA, high school class rank, ACT scores, and academic year. For the significance of this study, we have multiple stakeholders including universities, students, and policymakers. For universities, it helps the universities refine their admission policies by determining whether GPA, ACT scores, or high school rank serve as the strongest predictor of student success. Meanwhile, for students will gain valuable insights into the factors that significantly impact their chances of getting into university. And last but not least, policymakers can use the findings to determine whether more equitable admissions criteria are necessary.
Let's dive into multiple linear regression. Firstly, let's look at the model specification. Using correlation analysis, this is how we get high school class rank, ACT score, and academic year as the chosen predictor variables in this case. From the scatter plot matrix of high school class rank versus GPA, we could see that there appears to be a positive correlation between high school class rank and GPA. For ACT score versus GPA, there appears to be a moderate positive trend between the two. As for academic year versus GPA, there is no clear trend between academic year and GPA. However, academic year could indirectly capture changes over time with existing external factors like curriculum update, which might affect GPA trends. ID in this case is not a meaningful continuous predictor variables as it is most likely just an identifier. Hence, there is no relationship with GPA. Therefore, high school class rank, ACT score, and academic year are chosen as predictor variable for GPA, while high school class rank and ACT score show a positive correlation with GPA. Academic year is included to capture potential indirect effects over time. Next, the initial model fitting. Based on the chosen predictor variables, hence the estimated regression equation we obtain is y hat equal to negative 21.24834 plus 0.01005x1 plus 0.0371x2 plus 0.01128x3. The y-intercept, which is the b0, shows that when x1, x2, x3 are equal to 0, the predicted GPA is negative 21.24834. B1, or the slope, shows that for every 1 point increase in high school class rank, GPA increases by 0.01005, assuming all other factors are held constant. B2 explains that for every 1 point increase in ACT score, GPA increases by 0.0371, assuming all other factors are held constant. And B3 explains that for every 1 year increase in the academic year, GPA increases by 0.01128. Since the p-value equals to 0.4592, which is greater than alpha 0.05, suggesting that it is statistically insignificant, hence GPA does not change over time. Multiple linear regression is based on several key assumptions that must be met for the model to produce reliable results. This can include linearity, independence of errors, homoscedasticity, and normality. Based on these assumptions, we will only be checking the model adequacy based on linearity, homoscedasticity, and normality. Based on the scatter plot of residual predicted for GPA, the residuals are randomly scattered around the horizontal line at 0 with no clear pattern. This suggests that the relationship between high school class rank, ACT score, and academic year and GPA is linear. Hence, the assumptions of linearity is met, indicating that there is a linear relationship between the predictor variables and GPA. Next, the assumptions of linearity is met, indicating that there is a linear relationship between the predictor variables and GPA. This could suggest some degree of non-constant variance of errors, heteroscedasticity. Lastly, The QQ plot shows that most of the residuals plot lie along the diagonal line. This indicates that the residuals most likely follow a normal distribution. However, there are slight deviations at the tails, suggesting minor violations of normality. Hence, the normality assumption is mostly satisfied. Multicollinearity is when two or more predictor variables are highly correlated. Based on the output shown, the variance inflation factor values for all the variables are less than 10 and the tolerance values are greater than 0.1. This indicates that there is no serious multicollinearity in this case. Overall, the model meets the key assumptions of multiple linear regression. Linearity, normality, and homoscedasticity are satisfied. Hence, the model is adequate for analyzing the relationship between predictor variables and GPA.
Outliers and influential cases can significantly impact the results of statistical analysis, leading to biased estimates and misleading conclusions. Detecting and properly handling these data points is crucial for maintaining the integrity of a model. Outliers can be identified by using diagnostic measures such as standardized residual and student t residuals. In this study, 1 observation and 40 observations were identified as outliers using the standardization and studentization methods, respectively. Next, influential cases can be identified using diagnostic measures such as Cook's distance, leverage, defeats, and DF betas. In this analysis, 96 observations were identified by using Cook's distance, while 68 observations were identified by using leverage and defeats. Once the outliers and influential cases are detected, it can be managed through various approaches to ensure reliable statistical analysis, such as removal of variables and transformation of variables. In multiple linear regression, certain assumptions must be met for the model to be valid and reliable. These include linearity, homoscedasticity, and normality of residuals. If these assumptions are violated, transformation can help improve model adequacy by making relationships linear, stabilizing the variance, and normalizing the residuals. There are 3 types of transformation considered in this analysis, which is log, square root, and inverse. By comparing the results of log, square root, and inverse transformations, the square root transformation emerged as the best choice. It shows the highest R-square and adjusted R-square values, indicating that it explains the most variation in GPA. Interaction effects occur when the relationship between one predictor variable depends on the value of another predictor variable. Including interaction terms in a regression model helps capture these complex relationships and provide a more accurate understanding of how variables influence the outcome. These interactions test whether the effect of SAT score on GPA changes based on a student's class rank percentile. A high SAT score may not always result in a high GPA if the student had a lower class rank in high school, indicating differences in academic preparedness. So here is the results. Based on the results, since the p-value is smaller than 0.001, which is less than alpha 0.05, the interaction between high school class rank and SAT score is statistically significant. The effect of SAT score on GPA changes based on a student's high school class rank.
The conclusion of this study is, the study suggests that students with higher class rank and ACT scores tend to have better GPAs. However, ACT scores alone do not perfectly predict GPA since their effect depends on a student's background. Academic year has little impact, meaning curriculum changes do not strongly affect GPA. Outliers also suggest that other factors, like personal habits and support, may also influence academic performance. This study also used multiple linear regression to examine how GPA is affected by high school rank, ACT score, and academic year. The results shows that GPA increases with both high school rank and ACT score, while academic year has no significant effect. The model meets key assumption, though there is some slight heteroscedasticity. Outliers were found, and a square root transformation improved the model. An interaction between high school rank and ACT scores suggests that ACT scores influence GPA differently based on a student's high school performance.